The problem we aimed to address in this lab was whether the equation for kinetic energy is correct. In order to accurately measure the energy of objects in motion, provided equations must be proven. The given equation for kinetic energy is 1/2 mass times velocity squared. We wanted to experimentally prove that this is actually how the variables affect kinetic energy in real life. To do this, both the variables of mass and velocity must be examined individually. After conducting the experiment, we found that the theoretical final kinetic energy values were roughly equal to those that we calculated. So we concluded that the equation of kinetic energy equals 1/2 times mass times velocity squared is, in fact, accurate. This conclusion still stands when considering the possible errors present, which we will get to soon.
We based our experiment on the law of conservation of energy, which states that energy can neither be created nor destroyed, only transferred or converted. Accordingly, when an object is at a certain height above the ground and has a velocity of 0, all of its energy will be made up of potential energy, as shown in the top pie chart. This potential energy can be described in the equation energy equals mass times acceleration due to gravity times the height above the ground. As gravity accelerates the ball, it will reach a point the instant before it hits the ground when its velocity is greatest and all of its potential energy has been converted into kinetic energy, as shown on the bottom pie chart. The system schema on the right shows that the only two objects in the system are the ball and the ground, which act on each other with the force of gravity.
In order to simulate this model in the real world, we dropped balls of 3 different masses from a constant height, in addition to dropping a ball with constant mass from 3 different heights. The potential energy of each ball was calculated prior to dropping using the equation of potential energy equals the mass of the object times the acceleration of gravity multiplied by its height above the ground. For each of these 6 cases, we took a video documenting the entire drop, with meter sticks on the wall in the background to act as scales for height. From here, each video was analyzed using tracker. The distance between the 2 frames when each ball was closest hitting the ground was measured, and then the change in time obtained as a function of the frames per second. From this, the velocity of the balls were calculated and then inserted into the equation in question, kinetic energy equals 1/2 mass times velocity squared. At this point, energy calculations from this equation, as well as P equals mgh, were compared and found to be quite similar. However, there were 2 flaws in our experimental design. First of all, the frame rates the videos taken were not high enough to avoid motion blur, which caused difficulty in distinguishing where one location on the ball was from one frame to the next while using tracker. Second of all, the angle that the videos were taken at was not perfectly head-on, and therefore could have led to errors in scaling and tracker using the meter stick.
Here is the sample data that we collected from our experiment, as well as a sample calculation that shows how we calculated the kinetic energy of the rubber ball after being dropped from 1 meter. The velocity values that we used to calculate kinetic energy were determined using tracker, as mentioned on the previous slide.
The gravitational potential energy of an object is equal to the mass of the object multiplied by its height above the ground multiplied by the acceleration due to gravity. As mentioned, all of this potential energy will be transformed into kinetic energy as the object falls and its velocity increases.
By dropping objects of different masses from the same height, we were able to keep velocity constant and compare how varying masses affected the kinetic energy of the object. Additionally, by dropping an object of the same mass from different heights, which will change its final velocity, it can be examined if velocity is correctly expressed in the equation.
There are some possible sources of error that may have affected our results. First of all, the presence of air was not accounted for in our reasoning. Some of the kinetic energy that the ball gained would be transferred to molecules of air as it passed through them, so the actual final kinetic energy of the ball in our experiment would be less than its initial potential energy. Second of all, due to the limitation imposed by frame rates, the calculated velocity of the ball was not its instantaneous velocity, the moment before hitting the ground, but rather its average velocity over a short moment in time.